All right. What we're going to do today is we're going to start Chapter 19, which is amines. If you think about what we've done up to now, we have covered let me adjust this just a little bit. Okay. What we're going to do now is we're going to start Chapter 19. And if you want to think about what we've done, we started out covering alkanes, alkenes, and alkynes. Then we looked at the alcohols. Then in this semester, we looked at the aromatic compounds and the C double bond O. We're going to get back to the C double bond O's in Chapter 20 and 21 and 22. But we're going to stop for just a second and look at amines. Now, if you want to think about what an amine is, an amine is just a nitrogen with three things attached to it. Now, if all three of these things happen to be hydrogens, then this compound is ammonia. We can classify amines just like we classify alcohols and halides and all the other compounds. Now, the way we classify amines, though, is different than the way we classify alcohols. When we classify the amines, we don't worry about whether the R group is primary or secondary or tertiary carbon. What we do is we look at how many R groups are on the nitrogen. So if one of the hydrogens has been replaced, we call that a primary amine. If two of the nitrogens have been replaced, or two of the hydrogens have been replaced with R groups, that's a secondary amine. If three of the hydrogens have been replaced, that is a tertiary amine. And if we actually add 4 R groups, notice whenever we do that, we lose the lone pair and the nitrogen becomes positive. We call these quaternary ammonium salts. And quaternary ammonium salts, by the way, are really important today. If you look at most of the disinfectant wipes that you have, for those of y'all who are using disinfectant wipes, many of them contain quaternary ammonium salts on them as the disinfecting agent because they're very strong antibacterial agents or antimicrobial agents and everything. So the next time you look at the disinfectant wipes that you're using and everything, if they're not bleach based, they probably have quaternary ammonium salts in them. Now, naming amines is actually pretty straightforward. Okay? The easiest way to name amines is just the common name by looking at the groups that are attached to the nitrogen. Now, we did that before when we had this compound here. We call this ethyl methyl ether. When we had this compound here, we called it ethyl methyl ketone. Okay, so we've talked about these common ways of doing this. Amines are done exactly the same way by just looking at the R groups that are attached to the nitrogen. So if I have this compound, now notice that's not an aromatic ring, that's just a cyclohexyl ring. We call this cyclohexylamine. Now, we don't have to say anything about the hydrogens because it's understood that there are enough hydrogens to make 3 things attached to the nitrogen. So if I have this compound here, and I'm going to spread it out just a little bit. Notice in my notes, I have the CH3 written in parentheses twice, meaning there's 2 CH3s attached to the nitrogen. We would call this compound ethyl. And since I have 2 methyls, I would say ethyl dimethyl. Now, a little thing here that you should know. Notice that the ethyl still comes first in the alphabet, even though you think dimethyl should because it starts with a D. Remember, it's just the methyl piece that determines the alphabetizing. The di there is just telling you how many, and it's not part of the alphabetizing. If we have this compound here with 3 phenyl rings around the nitrogen, now I could have drawn that out where I had 3 different phenyl rings. We just call that triphenylamine. So the common way of naming amines is pretty straightforward. Now, the amino group, the NH2 group, is called the amino group whenever it's in a substituent. And we've seen that before. Whenever we were dealing with aromatic compounds, we talked about amino as a substituent. So if it's not the highest priority group in the compound, you name it as a substituent. So for example, if I were to just write this compound here, that's cyclohexene. But if I put the NH2 group on it, that's amino cyclohexene. The double bond gets the higher priority, so that's 1, 2, giving the amino at the number 3 position. So that's 3 amino cyclohexene. No number needed for the cyclohexene since it's understood to be 1 there. Again, when we get to this compound here, now several of y'all would miss this on the test. No 2 needed there. If I asked you to name this, what you would do is say the longest chain of carbon atoms is 2 carbons long. But notice I tried to trick you. The longest chain is actually 3. Notice we have an OH group and an NH2 group. So we have an alcohol and we have an amine. And again, using that table that's in the back of your textbook, it gives you the priority of all the different groups. And the alcohol is a higher priority than the amine. So we're going to name this as an alcohol, which means this carbon gets the number 1. And we're going to name it as a propane 1-ol. So that takes care of all of this piece. So what's left? This as a substituent. So it's just 2 amino propane 1-ol. That's all there is to this. Now, here's where it gets kind of a little bit complicated. Notice in every example so far, our nitrogen has been an NH2 group. That nitrogen can also be substituted. Okay, so let's look at this, and I'm going to draw it without the hydrogens. In the notes, it has the hydrogens. So we've got 1, 2, 3, 4, 5, 6 carbons with an OH there, and an N. And I've got 3 methyls in my notes. It should just be 2 methyls. And let's see, it's on the number 4 carbon over. So that's N with 2 methyl groups attached. Now, if that nitrogen had NH2 with 2 hydrogens attached, we would call it an amino group. So this substituent is called the dimethyl amino group. Okay, the dimethyl amino, because it's a nitrogen, so it's an amino group, but it has 2 of the hydrogens replaced with methyls. So if it had only been 1 methyl group on there, it would just been called the methyl amino group. So then we number it the same way. Okay, again, since it's an alcohol, the alcohol gets the higher priority. So this is going to be a hexane 1-ol. That takes care of all of this piece. And what's the attachment? We have a methyl amino group attached. And where is it attached? To the main chain at the number 3 carbon. So we have 3 dimethylamino, and then the rest of it is just like it would normally be, hexane, 1-ol. Okay, so don't make this any more difficult than it is. Let's look at another example. And again, let me show you a little trick that I've learned, and I'll show it to you on the next one. Now, if I were asked to name this compound, I could easily get confused. I know that this is my main piece because the ketone group is higher in priority than this group. So what I oftentimes think about is just how would I name that if that happened to be a chlorine? Notice we would name this as a cyclohexanone, and we would have numbered it 1, 2, 3, 4 chloro. So then I just say, okay, that wasn't a chloro, it was this piece. And then I just ask myself, what is this substituent called? And again, that is the ethyl methyl amino piece. Again, because it is a nitrogen that gives me the amino, and the 2 groups are different, so I put them in alphabetical order. Ethyl, methyl, amino as the group. So notice how I name it. 4 ethyl methyl amino, and then I just name the rest of the compound. Cyclohexanone. Again, no number needed here because this is understood to be the 1 position. That's all there is to naming these amines by the simple complex or simple way of naming these. Now, one of the things that you're going to be asked to do on the test is I'm going to say, name this compound as an aniline. On test 1, several of y'all named your aromatic compounds, and I wanted you to name them as phenols, or I wanted you to name them as toluenes or whatever, and y'all just went ahead and named them as benzenes. And that was fine because those are actually correct names. But on the 3rd test, I'm going to say, name this compound as an aniline. So you have to be able to do this. If I would have asked some of y'all to name this compound on the 1st test, y'all would have named it as aminobenzene, and that's perfectly correct. But the common name for this is aniline. So you need to know that. And then what we're going to do is we're going to put groups on here. So if that is aniline, and I asked you to name this on the test, I do not want the answer 1-amino 2-ethyl benzene. I want the name aniline, and if I use that, notice that's the 1 carbon and that's the 2 carbon, so that's going to be 2-ethyl aniline. You could also say orthoethyl aniline if you want to, or O-ethyl aniline. Okay, but I want it named as an aniline. Now, what if I had this compound? And I want it named as an aniline. Now, some of y'all would have named this as methylamino benzene. And that's correct. Does everybody see how that would be methylamino benzene? Because that is the methylamino group. But I want it named as an aniline. Now, when you name this compound as an aniline, What's different about it than the top compound? There's a methyl group out here. So you're just going to say methyl aniline. But you have to say where that methyl is. Notice if it was on the ring, we would use a number. But since it's attached to the nitrogen, what we say is capital N methyl aniline. So when we use capital N to show the position, that means whatever group we're talking about is attached to the nitrogen itself. Okay, so let's look at one more example, and let's look at this compound here. Again, some of y'all would have tried to have named this as an ethyl methylamino benzene, and that's perfectly correct. But on the test, I'm going to ask you to name it as an aniline. So the aniline takes in that piece there. So what we would say is there's the aniline. And then what's attached? An ethyl and a methyl. Where are they attached? Both of them are attached to the nitrogen. Okay, so we use N and N to show they're both attached to the nitrogen. Now let me give one other example here that's not in the notes. This came up in a discussion in one of my classes. Suppose we had this. Notice if we name that as an aniline. There's the aniline piece. What's attached to the aniline? 3 methyl groups. So what we have to do is we're going to say tri-methyl aniline. Now notice that 2 of the methyls are attached to a nitrogen, and one of them is going to be at the number 3 position. So what we say is N, N, 3. Okay, so when we have the same group on a nitrogen and the ring, we name it N. Since we have 2 methyls, we have to say N and N. Just like if we had 2 methyls attached to the same carbon, we would say 4, 4, you know, if it was in a straight chain. Okay, so it's N, N, and then 3. So it's NN3 trimethyl aniline. Okay, so naming the anilines is pretty straightforward. And again, on the test, I could ask you, name this as an aniline, so you can't use, you know, let me go and put that one back on the board just before we leave this. How else could you have named this? You could have named this as the dimethyl amino group, and then this would be the methyl group. Now in this case, the di part is part of the name of the group. So when you put this one, it's going to get the number 1, and this is going to get the number 3. Okay, so you would have said 1 dimethylamino, 3 methyl benzene. Or you could have named it the dimethylamino toluene. Okay, there's a lot of different ways to name this, but on the test, you're going to have to know how to name these as anilines. Okay, so make sure you can do that. The last little thing that we want to talk about is the IUPAC. All of the ways that we've talked about so far are the common methods. The IUPAC naming system says to do the thing. the same thing you did with alcohols. Find the longest chain, and then instead of changing it to OL, then change it to amine. So if we had this compound here, and I'm going to go back to the alcohols, okay, we would have named that compound 1, 2, 3, 4. We would have said butane 2-ol. Well, we're going to do the same thing. We're going to say again 1, 2, 3, 4. We're going to say butane 2-amine. So the IUPAC method does the same thing as the alcohols. So when you learn to name alcohols, naming amines is named the same way. And if there happened to be a methyl group on here, we would go back here and we would say N-methyl to show that the methyl is attached to the N position, N-methyl butane 2-amine. Okay, so when you name them by the IUPAC method, you name them just the way you did with alcohols, again, showing any groups that are attached to the nitrogen to be used. We use the capital letter N to show its position. So naming of the amines is not too difficult. Now on page 4 and on page 5, we're going to talk about chirality of amines. Now, I've often seen this question given as one of the first questions on a biochemistry test or a question on a PCAT test or something like that. If we look at this compound, and let's just look at a carbon compound. And I would ask you, is this carbon chiral? And you would say, yes, this carbon is chiral because it has 4 different groups attached to it. And you would say, okay, since it's chiral, we can have the R and the S in enantiomers. Now, what about amines? If I ask you the same question, and I'm going to draw this like this, there's a lot of different ways to draw this. And I were to ask you, is that compound chiral? The answer I would expect you to give me is yes, it is, because the nitrogen is chiral because it has 4 different groups around it. And you would be wrong. Although it has 4 different groups around it, that lone pair is not large enough to hold its space. So what this compound can do is it can rehybridize itself momentarily into an sp2 hybridized nitrogen. So that's just a momentary rehybridization. Now notice it's flat. Now it could flop back down and become the same thing that it started with, or it could flop up. And let me see how I want to draw that. With the lone pair down here. And if you notice what has happened, it's inverted. We can think of that as sort of an umbrella turning itself inside out in a windstorm. Okay? So because the lone pair is not large enough to hold its space, we can say the following. This compound is not chiral. Okay? Now, having said that, I want to ask you this question. So this is a question on your first biochemistry test whenever you take biochemistry. And I'm going to change it a little bit. And I'm going to put a CH3 group out here. Is that compound chiral? And based upon what we've said, you're looking at the nitrogen and saying, okay, there's 1, 2, 3 different groups around it, but the lone pair can't hold its space. So you're going to argue with me that this compound is not chiral. And congratulations, you just missed the first question on your biochemistry exam. Okay, this compound is chiral. The nitrogen is not chiral, but notice this carbon is still chiral. So when you're looking at the question, make sure you answer the question being asked. Not, is this compound chiral? The question you answered was, is the nitrogen chiral? Now, another way to put this question is, can this compound exist as 2 distereomers? And notice it cannot, because there's only one chiral center in the compound, so it can exist as a set of enantiomers. But remember, you can only have the diastereomers in these chiral centered compounds when there is more than one chiral center, okay? So for example, if both atoms were chiral, we could have had R and S, okay? We could have had R and S here, we could have had R and S here, and then we could have gotten enantiomers. And again, it's just something for you to remember. Now listen carefully. When you have the quaternary ammonium salts, going over to page 5, and I won't put this on the board, but the quaternary ammonium salts, the nitrogen behaves just as if it were a tetrasubstituted carbon with 4 different groups on it. So if you have that, then those compounds are chiral. So again, quaternary ammonium salts exist as both enantiomers. Now, to make matters worse, here's a question on the test. And again, not so much. Now, I'm going to show this lone pair coming out. Okay, normally we just show the lone pair on the atom, but I'm going to go ahead and show it coming out. And this is attached to a 3-membered ring. And on this 3-membered ring, we have a methyl group coming out and a methyl group going back. And I want to ask you, is this compound chiral? So let's look at the carbons. Is this carbon chiral? No, because notice it has 2 methyl groups that are identical. We don't show them, but these 2 hydrogens are identical. So this carbon's not chiral. And technically, this nitrogen's not chiral either. But in this case, it is. And the reason is, notice this nitrogen is in a ring. So it can't flip itself out the other way. So when you have these nitrogens as part of the ring, and the ring itself has got 2 different attachments, notice we've got 1 attachment to the nitrogen, 1 attachment, and 1 attachment. All 3 of those are different. The lone pair is different, so there are 4 attachments to the ring, and this one can't flip inside out. And again, there is a whole class of compounds based upon this fact that the nitrogen is in the ring and can't be flipped in and out. All the opiates come from a class of compounds where the nitrogen is in a ring system like this. Okay, so again, it unfortunately is not as, black and white as we would like it to be. We want an answer. Yes, it's either going to be chiral or not. So we've looked at three different things. Normally a nitrogen with a lone pair is not chiral unless for some reason it can't invert itself. Then it is chiral. And then we have to look at the rest of the molecule to determine whether the compound itself is chiral. What can we say about amines? They're polar. They're about as polar as ethers. Okay? If we have a nitrogen with one R group on it, notice we have a hydrogen attached to the nitrogen. That can hydrogen bond with itself. So primary amines can hydrogen bond with themselves. What about if we have two R groups on there? Notice again, we still have a hydrogen, so this can hydrogen bond with itself. So secondary amines can. But can tertiary amines hydrogen bond with themselves? And the answer is no, because there's no hydrogen attached to the nitrogen. Now they can hydrogen bond with water, of course, okay, but they cannot hydrogen bond with themselves. So therefore, whenever we're looking at boiling points, remember compounds that can hydrogen bond normally have higher boiling points. So notice on page 6, I've got three different compounds. I've got the amine, the tertiary amine. All of these compounds have basically the same molar mass. So when we're looking at these three compounds, the trimethylamine, again, I would expect you to be able to realize that the CH3 in parentheses tells me there's three CH3s attached. That one can't hydrogen bond to itself. Notice this is a secondary amine and it can hydrogen bond with itself. So we would expect its boiling point to be higher. Now, whoops, that's a CH3, sorry. Now on the next one, we have the alcohol. Now the difference in molar masses is not really the importance here. This does have a little bit higher molar masses, but not enough to matter. Notice it can hydrogen bond it also. But notice the difference in the boiling points between these three compounds. 3.5 degrees Celsius, 37 degrees Celsius. So just being able to hydrogen bond increases the boiling point. And this has a boiling point of 100 degrees Celsius. The oxygen hydrogen bond is a much, much stronger bond than the nitrogen hydrogen double bond or hydrogen bond. And again, in proteins, many of the proteins, the shape of the protein is determined by the hydrogen bonds that form. So whenever you start heating a protein and breaking those hydrogen bonds, so again, whenever you get into protein chemistry in your biochemistry classes, which bonds are going to break? It's the nitrogen hydrogen bonds that break first. Why? Because they're much weaker than the oxygen hydrogen bonds. So you can tell which bonds are going to break whenever you look at the denaturing of proteins later on in your biochemistry classes. And that's where the organic concepts really come into play. So what we have discussed up to now is the classifications of amines, the naming of amines, and then a little bit about the boiling points and the properties of it. What we're going to do with the rest of this section is we're going to look at the reactions of the amines. But before we get into that, we need to look at the basicity of amines. And again, it's very important that you understand how amines react. One of the things that is really makes amines versatile in organic chemistry is the fact that the nitrogen has a lone pair on it. So when we have an amine, it can react in an SN2 reaction as a nucleophile, kicking off the iodine. Now, we've seen this over and over and over again. Okay, that's just an SN2 reaction. Even though the amine is a neutral compound and not a negatively charged species, it's still a very good nucleophile because the nucleophile, remember, has to donate its electrons, and nitrogen electrons are very donatable. So what's the product of this? RNHH, I'll just draw it out a little bit, hooked to the CH3, and then the iodine gets kicked off as the negative ion. Notice that the nitrogen has 4 things around it, so it becomes positively charged. And then later on, we can pull off one of those hydrogens with a base if we want to. So this is the reaction where the nitrogen acts as a nucleophile. What we're going to discuss in the rest of this section, though, is we're not going to discuss nitrogen acting as a nucleophile. We're going to look at the reaction of nitrogen acting as a base. Now, if I asked you, what's the definition of a base? Now, you don't have to unmute your mics. Just say it out loud wherever you are. What's the definition of a base? Think back to your general chemistry. What's the definition of a base? Most of y'all probably said something to the effect of this. A base is anything that can accept a proton. And that's what you learned in general chemistry. And that is exactly right. Except that's not going to help us in organic chemistry. What we're going to do is define a base as anything that can donate electrons to the proton. And you say, but that's the same thing. You looked at it from the proton's point of view. The base accepted the proton. How did it accept the proton? By donating its electrons to the proton. So in our definition of nitrogen behaving as a base, we're going to say the nitrogen behaves as a base because it donates the electrons to the proton. And that's going to be slightly different than your definition. But that slight difference will help explain all the organic things that we're going to talk about. So if I had the reaction RNH2 reacting with HX, I'm going to put my lone pairs on here. Notice what happens. This donates the electrons, kicking that out. We've seen this reaction 100 times in general chemistry. Probably the reaction your instructor wrote was NH3 plus HCl. And what did it do? Gave us NH4 plus Cl minus. Isn't this the same exact reaction as that? Because the only difference is we've got an R group in place of one of the hydrogens. So amines behave exactly like the chemistry of ammonia in their acid-base properties. Now listen carefully. We're going to put a bunch of gibberish on the board. You're not going to have to do any of these calculations. I know all of you love these Ka and Kb calculations whenever you took general chemistry, but we're not going to do any of them. We're going to apply what we learn from this, but we're not going to actually do any of the calculations. So if I have a base, and in this case, that base is an amine, and I were to react it with water, we can draw the following equilibrium. This acts as the base, this acts as the acid. So the product is RNH3 plus, whoops, no long pair, plus OH minus. Now, if that is an equilibrium, we can write an equilibrium constant for it. And we can say that Kb equals the RNH3 plus concentration times the OH minus concentration over the RNH2 concentration. Now, that's exactly what you learned in general chemistry. You learned that if you take a base, react it with water, it gains a proton. Now, let's see what we can say about this equation. It's an equilibrium. It's always the products over the reactants. So the larger the products are, the further the reaction proceeds to the right. The larger the products are means the larger the numerator of that fraction is. So Kb is larger. So the larger Kb is, the further the reaction proceeds to the right, the stronger the base. Okay? Now, we also know that pKb equals the negative log of the Kb. So the larger the Kb, because of this negative sign, the smaller the pKb. So here's the thing that comes out of this. The larger the Kb, the smaller the pKb, the stronger the base. And normally we don't talk about Kas and Kbs. We talk about the pKas and the pKbs. And the relationship between pKa and pKb is at the bottom of the page. They add together to give 14. So if we know the pKb of the base, we also know the pKa of the protonated form of the base, the acid. Okay, but listen carefully. The smaller the pKb, the stronger the base. Now that's important. That's what we should have got out of that page. Now, let me ask you a question. If I'm given two different bases, can I tell which base is the stronger base? For example, here would be a good test question. Now listen to the answer, okay? CH3NH2 versus HNH2. We could have written that as NH3. Which one is the stronger base? Now listen carefully to answer these questions. Whenever you get into questions about which ones are the stronger bases, what's the definition of a base? Anything that can donate electrons. So if I'm wanting to determine which one of these is the stronger base, the answer is very, very simple. Which one can donate its electrons more easily? Now you might think this one is because it's less sterically hindered. Normally, steric hindrance doesn't play a part in basicity because you're donating the electrons to a hydrogen atom, which is very, very small. So usually the answer is not steric hindrance. But if I look at this, remember a long time ago, we said that methyl groups can donate electron density via the inductive effect. Hydrogens do not do that. So listen carefully. This methyl group is donating electrons toward the nitrogen, putting more electron density on the nitrogen. If the nitrogen has more electron density, it can donate its electrons more easily. So because this methyl group donates electron density, notice it's going to be the stronger base. So if I look at these have a pKa in your notes of 4.74 and 3.36. Notice that the ability of that methyl group to donate electron density makes that base over 10 times stronger base. Okay, so anything that makes the electrons more donatable, in this case, electron density being donated to the nitrogen, increases basicity. Okay, and that's very, very important. Primary, secondary, and tertiary amines all have about the same basicities, and they're all more basic than ammonia. So one group donating in really doesn't make that big of a difference between two groups donating in. Now we're going to look at something that we've already looked at, and I'm going to put 4 compounds on the board. Okay, and if you haven't yet, don't turn to page 9. Okay, because these 4 compounds illustrate what I want to talk about. Okay, so we have a 5-membered ring. We have a nitrogen in the ring hooked to a hydrogen. In this case, I have 2 double bonds. Same structure without double bonds. Then we're going to look at this compound. Well, and I'm going to go ahead and show these with the double bonds. And then I'm going to look at this compound. Again, with no double bonds. And I'm going to ask you on the test, which one of these compounds is most basic? Which one is least basic? Okay? Now, let me ask a question. Do you agree that on each one of these nitrogens there is a lone pair? That's the first question. The second question is, does the lone pair go inside the ring or outside the ring? Remember, the only time we put a lone pair inside the ring is if it is needed for aromaticity, and y'all got finished doing that on your first test. So by placing this lone pair inside the ring, it's part of the aromatic ring. Notice, whether we place it inside or outside is not going to make that aromatic, so we leave it outside. Now notice this one already has enough electrons for an aromatic ring, so it's going to be on the outside. On this one again, there's no aromaticity because these are not sp2 hybridized carbons in the ring, so it stays outside the ring. Since these electrons are tied up in the aromatic ring, they can't be donated. Because in order to donate these electrons, we have to destroy the aromatic ring. Therefore, this is the least basic of all. And if we look at the pKa, or excuse me, pKb, pKb is about 15. Very non-basic. Now, if we look at this one, it's 2.73. Notice how many times more basic. Let's make that 3 so we can do the math. This is 10 to the 12th times more basic than the compound above it. 10 to the 12th, not 12 times, 10 to the 12th. Okay? A big difference in basicity. Now, what's the difference between this compound and this compound? Notice on this one, the lone pair, the nitrogen is sp3 hybridized, and on this one, the nitrogen is sp2 hybridized. So whenever we're looking at electrons that are not in the aromatic ring, we look at the hybridization of the nitrogen normally. So this is sp2 hybridized, sp3 hybridized. And we've already said that the electrons on an sp2 nitrogen, if we want to think about that, that's 33% S, 1 out of 3 parts. This is 25% S. Okay? These electrons have more S character, which means that nitrogen atom is holding those electrons more closely to the nucleus. If it's holding the electrons more closely, notice it's not donating and sharing the electrons. So this one is going to be less basic than this one. And it turns out that this is 9.40. Again, this one and this one are about the same, and this is 2.88. Now, I would not have expected you to be able to tell whether this one or this one was more basic. Notice they're pretty much basically the same basicity. So, when you're asked to compare bases, make certain that you look at whether the electrons are donatable or not. And there's two ways to easily tell. Okay, one of them is what? Are the electrons tied up in the ring or not? The second one is the hybridization. Now I'm going to erase these and then I'm going to put one of them back on the board. If we were to look at these two compounds here, without going over to page 10, and again, I'll use the single bonds in there. We know that we can draw the little circle, but I'm going to use the bonds. Which one of those compounds is more basic? This has a pKb of 9.40. Would you expect this compound to be more basic or less basic? Okay, I want you to answer out loud at your house. You don't have to unmute your mics. Is it more basic or less basic? I would expect it to be much more basic. Why? This is an sp2 hybridized nitrogen and this is sp3. But whenever I actually calculate the pKb of this compound, they are exactly the same. Why? Why are these two pKbs the same? Now, this is something that you need to understand about chemistry. And nobody likes this about chemistry, but you need to understand it about chemistry. Whenever something is not the answer that you expect it to be, you've done your calculations, you redid your calculations. Something is not what you expect, then the answer has to be something. And that's what students don't like to hear. Why does this not follow the rules? And there has to be a reason for it, okay? So when something like that happens, then you have to be able to understand why. And what most of you do is you just say, I'll wait for somebody else to explain it. But for those of y'all who are going into a science field, that's where the breakthroughs come in, is whenever something doesn't behave the way we expect, and then we explain why it behaves differently. And the reason is, I can draw resonance structures for that. Now watch this resonance structure. I can put that there, and then that pair of electrons there. So that resonance structure looks like this. Now the nitrogen has a positive charge and that carbon has a negative charge. And if I were asked you on the test which one of these two resonance structures is more important, you would say this one, because it has no charge separation. But this resonance structure at least is somewhat important. Now we can go through and move this pair of electrons down and this pair of electrons up to get this resonance structure. Now the negative charge is on this carbon. And we can draw a third resonance structure, moving this pair of electrons down and this pair of electrons over to draw something that looks like this. Now the negative charge is on this carbon. Now the reason those resonance structures become important is, notice, In each one of those three resonance structures, what's the hybridization of the nitrogen? It's sp2 hybridized, but notice also that the lone pairs are tied up. They are part of the resonance structures. Notice the nitrogens do not even have a lone pair to share. So the importance of these resonance structures is so important that it lowers the pKb down to what a normal sp2 nitrogen would have. Because notice these three do not even have a lone pair to share. Okay, so the fact that those lone pairs are tied up in resonance decreases the basicity. Okay, so whenever you see a nitrogen atom attached to an aromatic ring, it's not as basic as you would think it would be. And again, this comes into play when we get into amino acid chemistry and everything later on. Okay, now what about the different anilines? Okay, so we said aniline itself has a pKb of 9.40. I want to ask you this question, and again, these are all on page 10, but don't just look at page 10 for the answer. As I go through these, again, just say to yourself what you think. Is this compound that's a CH3 group, is it more basic or less basic than just regular aniline? Now, what you have to ask yourself is, remember when we were doing our aromatic compounds, we said that that methyl group can donate electron density via the inductive effect? Okay, so if it can donate electron density in, notice it's pushing electrons toward the lone pair. Notice it should make the lone pairs more donatable. Therefore, what? It should be more basic and therefore have a lower pKb. And notice the pKb is 8.92. So it's not a lot more basic, but it is somewhat more basic. Now, what about if I put an NO2 group on there instead of a methyl group? Notice that the NO2 group we learned whenever we were doing aromatics is an electron withdrawing group. So therefore it does what? Pulls electron density away from that lone pair, making that lone pair less donatable. Therefore, what should happen to the pKb? The pKb should go up. It should become less basic. And notice it's 10,000 times less basic. Okay? Now, what about an OCH3 group? Whenever we were doing aromatic chemistry, we said what? The OCH3 was a donating group, but it didn't donate via the inductive effect. It actually donated via resonance. Remember, we had two extra resonance structures for that one, okay? Or one if we had the pair position. So it can donate via resonance. So not only can it donate electron density more, or donate toward the nitrogen, it does it even better than the methyl group. And notice this is 8.7. So it's even lower than the methyl. So I could give you those compounds on the test and ask you which is the most basic and which is the least basic. Now notice whenever we put the methyl groups on the nitrogen themselves, okay, when we put the methyl groups on the nitrogen themselves, it doesn't lower the pKb as much. If you're looking on page 10 now, if we're looking at this compound here, where we put the methyl group on the nitrogen itself versus where we put it on the ring, This has a pKb of 9.1. Notice the methyl group up here can donate electrons better than the methyl that's directly attached to the nitrogen. The ring structure allows these electrons to be donated very, very nicely. So, what can we say about basicities? The aniline compounds are basic, but not as basic as we would expect because of the resonance stabilization of the lone pair. And of the aniline compounds, putting different substituents on there, we can predict which substituted aniline is more basic. So what we've looked at is the basicity of the amines.